Okay, this is sample problem 9.3. Hydrogen selenide. H2SC is a foul-smelling gas that can cause eye and respiratory tract inflammation. The HSE-H bond in the H2SC is approximately 92 degrees. Use valence bond theory to describe the bonding in this molecule. So what we're going to do is we're going to take note that we have a selenium atom, a hydrogen atom, and a hydrogen atom. So we begin by drawing the Lewis structure. Selenium is in group 6A, so it has 6 valence electrons. The hydrogens are in group 1A, so they each have 1. So that's 8 electrons. We've already used 4. So we'll just do an octet for the selenium. Okay? Now, the key to this problem is they're telling you the bond angle. From Vesper theory, we might predict the angle here to be bent, like water molecule. So we might expect the angle to be around 105 degrees. 104.5 is the bond angle for water. But they're telling us it's not. It's actually closer to 90 degrees. It's very close to 90 degrees. It's 92. That's a right angle. It's certainly not 104.5. So what's going on here? The argument we would make is the following. If we consider the central atom selenium, selenium's valence shell is 3s with 2 electrons, 3s2, I'm sorry, my mistake, it's 4s. Sulfur would be 3s, so it's 4s2, 4p4. Now it's true there's also 3d electrons, but those are in an earlier shell. We're talking about the valence shell, so the outermost quantum number, principal quantum number n. So there's our electron configuration for selenium. Now hydrogen is very, very simple, right? Hydrogen merely has one little orbital, the 1s orbital with 1 electron in it, right? So here's what we would argue. There are 2 hydrogen atoms, each with a 1s orbital with 1 electron, right? 1, but 2 is better, right? Chemical bonds generally have 2 electrons. Where do you see individual electrons? Not pairs, but individual electrons in the selenium. They're over here in the 4p. So the argument that we would make is that what happens is these 2 orbitals interact with each other and they undergo some sort of overlap. And then these 2 orbitals interact with each other and they undergo some sort of overlap. These orbitals here are already filled, so they don't have room for electrons anyways. So what happens is that if you consider these 2 orbitals, this one and this one, those are 4p orbitals. Remember what we said about 4p orbitals? Back in chapter 6, toward the end of it, or about p orbitals. P orbitals have 3 possible orientations. So one orientation is like this, but then the next orientation, we might call this, I'm not going to give it a name, the next orbital, 4p orbital, or whatever kind of p, is 90 degrees rotated, right? Essentially what I did was I rotated this orbital here by 90 degrees in order to get this one right here. Okay? So these are perpendicular to each other. Right? Think of a xy axis. You got one orbital here, 90 degrees to that is this one right here. So if you rotate one of them 90 degrees, you get the other one. That's essentially what's happening here. One of these 4p orbitals is perpendicular to this one. So when this orbital overlaps with this orbital, it forms a bond. These 2 electrons pair. When this orbital overlaps with this orbital, those 2 electrons pair and you form a bond there. But this orbital is perpendicular to this one. So here's what you end up with. oops, you end up with the selenium using one of its 4p orbitals, right? So that's a 4p orbital, and it has one electron in it, and then that overlaps with the 1s orbital from the hydrogen atom. So there's your hydrogen, and that's your 1s orbital, okay? That one also has an electron in it. So what happens is those two electrons occupy the same region, this overlap region, and there's your bond. So this part of the orbital is not even used. It's empty. It's not empty. It actually has some electron density in it, but the bond is up here using this lobe from the 4p. But now there's another 4p orbital in the selenium. I drew that a little too big compared to the other one. It should be pretty much the same size as the first 4p that I drew. Okay, so here's your 4p. I'll write it over here. And then what happens there is you get overlap with the 1s. Boop, 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 boop. And then same idea. You now have two electrons. They pair up to form a bond. This is our overlap region. And that's a bond. And this over here is an overlap region. And that's a bond, right? So there's two bonds, but those two bonds are 90 degrees apart, approximately. Now, in fact, it's 92 degrees, so it doesn't match up perfectly with the p orbitals. P orbitals are from 90 degrees, but it's pretty close. So that tells us that primarily these two bonds are driven by this valence theory, which is the idea that the bond is the overlap of these atomic orbitals, the 4p orbitals in this case, with the atomic orbitals that are available for the hydrogen atom, which would be the 1s.